Okay, so we've got this result here. Where on earth does it come from? This result's only true for independent random samples from normal distributions with equal variance, equal standard deviation, but just where did I get that from? Well, I guess the first thing we should think about is how that relates to what we've already seen for one sample tests. So if you had one sample, one random sample, we know that this statistic here has a t n-1 distribution. It looks a little bit like this one. Instead of sample means, we got sample mean differences. Instead of true means, we got true mean differences. Instead of s on root n, we've got this thing here. You can think of s on root n as like s times root 1 on n. And so we've got like s times root the sum of the 1 on n's, okay? So it's kind of, the bottom looks a little bit like the bottom. And the other thing that's going on, if you look at the degrees of freedom, you can think of the degrees of freedom as the sum of the n-1s across the two groups. So we got n1 minus 1 plus n2 minus 1. So if you sum the n-1s for the two groups, you end up with n1 plus n2 minus 2, okay? So the degrees of freedom here, you can see as n-1 for two samples, for two independent samples. And the SP, root 1 on n1 plus 1 on n2, is like a s root 1 on n, like summed for two samples, summing inside the square root sign. Okay, so we can see from looking at these things that they're kind of similar, but like, okay, where does it actually come from? Well, where did this result come from? We started off by saying that if you've got a normal random sample, if you've got a normal random sample, the mean is normally distributed with mean mu standard error sigma on root n. Okay? We started there, and this remains approximately true. Remains approximately true by the central limit theorem for data from any random variable. So anyway, x bar minus mu over sigma on root n then has, well, if we standardize, we subtract by the true mean, divide by the standard error, we get a statistic that tells us how many standard errors our data are away from the true mean, and that ends up having a standard normal distribution. In life, we don't usually know the true standard deviation, so we estimate it using S, the sample standard deviation. S squared is a statistic which satisfies this equation here. And then if we just replace that, replace the sigma with S, we end up with this result, we end up with this statistic here, which can be shown to exactly have a Tn-1 distribution if your data is normal. So if your data is normal, that's exactly normal, this is exactly normal, this is exactly Tn-1. If your for any distribution though, by the central limit theorem, this guy is approximately normal, which makes this approximately normal. And well, this ends up being approximately true as well for data from, if your data aren't normally distributed. So that's what happens in one sample. What happens in two samples? Well, it's going to get a little bit messier, but we can derive more or less this stuff all using what you already know. So we're interested in the sample mean difference, okay? We're making inferences about the true mean difference from the sample mean difference. We need to know the distribution of this thing. Well, if we got two independent samples, each of them are normally distributed, what do you reckon the distribution is of a sample mean difference? Normal distribution, well played. Well played. So because this is a linear combination of normal random variables, any linear combination of independent normal variables is normal. So by the central limit theorem, if this is approximately normal, then by the central limit theorem, this is going to be approximately normal for data from any distribution. If our data was exactly normal, this is exactly normal. What is the mean and standard error of this guy? Well, you can use standard results from random variables to say that if you've got a difference between two random variables, the value that difference is centered around is the difference of the centers of those two random variables. Okay? That's a standard result that we've seen earlier in the course. Expected value of x minus y is expected value of x minus expected value of y. And this one here, we know that the sample means are centered around the true mean for each of these groups. So for the first group, we get mu1. For the second group, we get mu2. So we can say that sample mean difference is normally distributed centered around this, true mean difference. What's the standard error? Well, the standard error is always the square root of the variance. What's the variance of a difference? Is it the difference of the variances? Can I just do the same thing? Is that legal? No, that is not legal. The variance of a difference ends up being the sum of the variances. Remember there was this result? Remember this result we had? That like variance of ax is a squared times variance of x. So you can think of negative x bar 2 as being minus 1. So this is like x bar 1 plus negative 1 times x bar 2. And so you square that negative 1, it turns into a plus 1. So that's one way of thinking about where this plus comes from. So what is the variance of x bar 1? What is the variance of x bar 2? We know this. We know that sample means have standard error sigma and root n, so their variance is sigma squared on n. If we got a sample of size n1 for the first group, we got sigma squared over n1. If we got sample size of n2 for the second group, we're talking sigma squared on n2. We could rewrite that as sigma squared times 1 on n1 plus 1 on n2. Okay, so there we go. This is the distribution of a sample mean difference. And this is the argument we made to get that result based on just standard results for random variables. Is this always true? Can we always say variance of a difference is the sum of the variances? It's not always true. There's often a covariance on here. We need to assume that these two things are independent of each other in order to get this result. So this here is only true. It's only true if x bar 1 and x bar 2 are independent. So there was an assumption when we use this result that we had independent random samples. We need independent random samples in order to be able to say that the standard error of a sample mean difference has this form. If we didn't have independent random samples, we couldn't have just done this plus and got to this form. It's only true for independent samples. So we got to this point. We're not quite at that point there. We can use the same arguments as before. So first of all, we standardize. So if sample mean difference has that form, then I can subtract off its mean, divide by its standard error, and that gives me a standard normal. I don't know what the true standard deviation is. I'm going to replace it with some estimate from samples. And when I replace it with this particular estimate, I end up with a t-distribution. So the way this estimate works is, it's the same as this formula here, except I sum the numerator and sum the denominator. So I've got a sum of xi minus x bars. I got a sum of that for each group. Okay, so I'm summing that for each group, and then I'm dividing by the sum of n minus 1 for each group. Now, this you can think of as, okay, so because s squared has this form, you can think of the sum of squared deviations from the mean as s squared times n minus 1. So this here is s1 squared times n1 minus 1. This part here is s2 squared times n2 minus 2. You can simplify this expression, write it as n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. And that's pretty much all there is to say about where this formula here comes from. Whew!